All right. And then I'll let x3 equal to z. So check it out. What's x1 prime? Or dx, well, let me write x1 prime because dx1 dt is a drag. x1 prime is y prime, right? But what's y prime? X2, yes. And let's see here, what's x2 prime? That is y prime prime, which is, if you solve this, minus 3y prime minus 4y plus e to the t, right? Solving my first differential equation for y prime prime. And so what do I get there? So, in other words, x2 prime is equal to minus, what was y1 prime? This is y is x1, so minus 4x1 minus 3x2 plus e to the t, right? I'm going to box the, rewrite these x1 prime equals to x2. So I've got this one, now I've got that one. This translates into what? This is x3 prime is going to be what? It's z prime. Z prime is the what? Z prime is cosine t minus y, right? Or minus y plus cosine t, aka minus x1 plus cosine t. In other words, just to recap, x3 prime is equal to minus x1 plus cosine t. Let me circle that. Put these together, you got yourself x1, x2, x3 differentiated is equal to, what's my matrix? My matrix is 0, 1, 0, minus 4, minus 3, 0, minus 1, 0, 0. That's whack. Okay, x1, x2, x3, plus what's my 0, e to the t, cosine t. So check it out. We started with a second order differential equation and a first order differential equation, a system of mixed orders. But after we make the reduction of order, we've got a system of 3 first order differential equations in normal form. And if you search your heart, you realize that if I give you any collection of linear differential equations of various orders, right, ordinary differential equations, you can always make this systematic introduction of new variables to remove derivatives. And because of the linearity of the problem, you can always just sort of sort through these and list them as one grand glorious list of first order differential equations. Right. Question, yeah? Well, I mean, y and y prime. So, I mean, that's the... These are not really independent if you go back to y, are they? I mean, I can get y prime from y by differentiating, can I?
You could have y and y prime be linearly independent, could you?
I suppose.
Y equals...
I'm not sure I know what that means. I mean, I'm just going to have to agree to not understand at the moment. Not saying that your question doesn't make sense. I'm just saying I don't know how to understand it yet. Let me think about that. Anyway, do you guys agree that we can take any system of differential equations and make this reduction of order? So basically, if we can solve the star equation, we can solve any of these, is the point. Right, so that's why we're going to put so much effort into how to solve the star equation over the next couple lectures. Right? But before I get to that, let's do a little bit more calculus of matrices, all right? I'm not going to solve this. Okay, don't. So a little bit more on the calculus of matrices. check this out. If we take the derivative with respect to time of a times b, it works out to dA dt times b plus a times dB dt. Now you're like, hold on a second, how do you differentiate? What do you mean dA dt? What is that? So here, a matrix of functions has dA dt. All right, so how are we going to do this? dA dt, the ijth component, guess what it is? The definition, hold on, it's really complicated. So it's dAij dt. I know that doesn't look like I said anything, but I really said something. I'm saying that you calculate the derivative by differentiating component-wise. And we could also talk about the integral of a dt. Likewise, that's defined to be the component-wise integration, all right? So we have differentiation and we have integration of matrices of functions. And you'll allow me this calculation here, for it gives me joy. K equals 1 to n aik bkj. So here we're looking at the derivative with respect to time of the ijth component of ab. All right, so ijth component of a times b, assuming that a and b are multipliable matrices of functions, I have this formula, and then, but what's the derivative of a sum? Finite sum, right? It's the sum of the derivatives, right? And, right, so the derivative sum is sum of the derivatives. Now, we're looking at the derivative of a product of two real functions. So we have the product rule, right? So this is by the ordinary product rule n times. I mean, it's applied n times, one for each thing in the sum. I'm applying the product rule n-fold times. But then, this is exactly dA dt times b plus a times dB dt, the ijth component of that. I could break it into two sums, but I think I've written enough. So the point is that identity comes from just the ordinary product rule and the fact that matrices multiply in a way which is consistent with that. But you got to be careful. You can't. You have to respect the order here. It's important that A goes first and B goes second. Right? I think that's the main one I need for our work in here. That's pretty much all I need, if I remember right. And if we need anything else, we'll derive it when we get to it. How about that? All right. There's, of course, theory I should cover. I guess we'll have to cover it next time, but I mean, I didn't want to cover it this time anyway, don't get me wrong, but if you don't mind, in the remaining, say, 5 minutes, let me just show you one of our major calculational techniques. All right, so how to solve dx dt equals to ax. I'm just going to run through this. Won't be the last time I do this, but just the first time I do it, okay? How about this? What if we let x of t be e to some power of t, right? But now that's not going to work, right? I mean, this is like, see, why is this a reasonable choice? Is because this is a lot like dy dx, right, equals to ay, right? And you know the solution to that is y equals what? E to the ax, right? It's a lot like that, right? So here, e to the lambda t is kind of a natural thing to try here. I mean, maybe you want to try e to the at, but then you got to make sense of what does it mean to say e to the matrix times t. Does that make any sense? Right? It does. Anyway, sorry, the cough, but that's for later. So in the meantime, we'll make this rather lowbrow assumption. This is the so-called eigensolution. It's not clear why we would call it that yet, but this is sort of the most naive sort of thing you might try. And if this is this is a guess, all right? So let's see here. If that's going to solve the differential equation for a given a, what do you need? You need dx dt, right, to be equal to a times x. So dx dt is what? It's d dt, right, of e to the lambda t times u, right? So by basically that product rule I just worked out, you could look at it as a special case of that if you want. This is d e to the lambda t dt times u plus e to the lambda t times du dt. I'm assuming here that u is just a constant column vector, though, okay? So this is just 0. In other words, the u just rides along. So the derivative is just lambda e to the lambda t times u, all right? So that's the differentiation. And then on the other side, this goes to just a e to the lambda t times u, right? So we want these to be equal, right? We want this to be equal to that. So that gives us this condition, a e to the lambda t times u equals lambda e to the lambda t times u. I think this marker, I love this marker, but I have to admit it's dead. Actually, I mean, the color of it does give me pause, for it represents the school of great evil. But au is equal to lambda u. This is the condition we need on the lambda and the u. Do you guys know what this is? Oh, what was his name? I'm trying to remember. Well, I shouldn't say it anyway, but the student who's currently missing, which is easy enough to miss in here, has had linear algebra before. He should recognize that this is the condition that u be an eigenvector with eigenvalue lambda. So eigenvectors give us solutions to these differential equations. So a large part of the story in here is going to be finding eigenvectors, because every eigenvector we find is going to give us a solution to the differential equation. For example, if I had x prime, y prime is 1, 1, 1, 1, xy, like this, I can tell you an eigenvector of this has, if I look at u equals to like 1 minus 1, that's an eigenvector of this, because if I multiply a times that, sorry. See, because if I do 1, 1, 1, 1 times 1 minus 1, what do I get? No. 1 minus 1, 0. And 1 minus 1, 0. So that tells me that if I look at x vector equal to e to the, this is, by the way, 0 times 1 minus 1. So the eigenvalue is 0. So if I look at e to the 0 times t times 1 minus 1, aka 1 minus 1, this is actually a solution to that differential equation. So the constant solution 1 for x minus 1 for y solves that differential equation. Because x plus y is equal to x prime, which is 0. Although that differential equation sort of violates my previous condition on independent equations, but it's okay. I'm dropping that now that we're to the normal discussion. Okay. That my insistence on independence was just for counting purposes earlier in this lecture. We can have matching rows. It just actually makes problems easier. Now, I think there's another eigenvector here. Can you see anything else I can multiply by 1, 1, 1, 1 to get back a scalar multiple of that self? Let's see, the trace of this matrix is 2. The other eigenvalue is 2. If you look at W, or let's say U2, equal to 1, 1, you can easily check that. Sorry, I'm writing all over the place here. A times U2 is equal to 2, 2, which is 2 times 1, 1. So that tells me I have also a solution x. The second solution is e to the 2t times 1, 1. That's also a solution. In other words, x equals to e to the 2t, y equals to e to the 2t. That also solves this. It's easy enough to see that's true. E to the 2t plus e to the 2t is equal to the derivative of e to the 2t, which is, by the way, 2e to the 2t. So this is another solution to that differential equation. I found it because I found the eigenvector of 1, 1, 1, 1, 1. How many ones? I don't know. Anyway, we're going to spend 2, maybe 3 classes on eigenvectors in here, so hopefully we'll demystify these things. Of course, I do need to talk to you about the theory of systems before I get far into that, and I'm sorry I went over time, but in my defense, I couldn't start on time. Thanks, guys.